right, this video is on phase diagrams, what a phase diagram is, how to read one, and what other pieces of information we can collect from looking at the phase diagram of a particular substance. So what is a phase diagram? Well, for starters, they look like this. Okay, so they are kind of a graph. But it shows the relationship among the states of matter for a substance. Okay, so actually it shows, I should probably be more specific and say it shows the pressure and the temperature that particular substance exists as a solid, a liquid, and a gas. Okay, it also shows boiling point, melting point, and you just have to know how to read the graph to figure out those pieces of information. Okay, and there's kind of a lot of information contained in a phase diagram, and so we're going to look at the phase diagram for water. Now, this is obviously not to scale, okay, but this is what the phase diagram of water looks like. The first thing we have to do when we think about phase diagrams is to identify which state of matter goes in which section of the graph, okay? And it always goes like this. This is the solid, this is the liquid, and this is the gas. And you can think about that because the higher the temperature, right, should probably belong to the gas state for that particular substance. And so that's always how it goes. Solids on the left, and then you work your way from solid, liquid to gas for a phase diagram. So for, since this is H2O, then the solid is ice, the liquid is water, and the gas is steam or water vapor. Okay, so a couple things to discuss in this graph. So the first one is this point where the lines seem to meet. Okay, and so I'm going to kind of draw an arrow. This is called the triple point. It makes sense that it's called the triple point because it's the converging of the three lines. So the triple point is defined as the pressure and the temperature, okay, where all three states of matter exist in equilibrium. So meaning they would exist together at the same time. Now, that might kind of baffle your brain because you're probably thinking, well, I've never seen ice, liquid water, and steam exist all together. Well, and you're correct. And the reason you haven't is because the temperature is about 0 degrees Celsius. Well, that's achievable. That's just, 32 Fahrenheit. That's freezing, right? But the pressure, look at the pressure. The pressure is almost non-existent. And so to achieve the triple point of water, you would almost need a vacuum situation where you have pumped out almost all of the pressure. And so it can be done. It has been done. And there's videos on it, and we'll watch a video on the triple point, but we would never see the triple point because if you think about it, right, what's normal atmospheric room pressure, it's about 1, and so we're nowhere near the triple point in that situation. Okay, but every substance has a triple point, and it's just going to vary based on if it's what type of substance it is. Okay, so again, it's just a condition of pressure and temperature where all three states of matter coexist. So that's actually kind of a cool thing to think about. The second point that's worth talking about is called the critical point. And the critical point for a substance is the pressure and the temperature, okay, beyond which there's no distinction between liquid and gas. This is also weird to think about. Okay, but it basically means that beyond that point, we really can't talk about H2O being a liquid, and we really can't talk about H2O being a gas, because there's really no distinction of the two, because the line doesn't continue. Okay, but again, think about this. The temperature is quite high, 374 degrees Celsius, but look at the pressure, 218 atms. Holy cow, that's monumentally large. So the critical point is something that we're never going to see for something like H2O. So then the other thing to be aware of is, like I said, we can talk about boiling point and melting point or freezing point. And so we've discussed before that the term normal, okay, the normal boiling point, the normal freezing point is those temperatures at 1 atm. And so what you can do is take the 1 atm line and extend it until you hit the solid liquid line, okay? Because, as we're progressing through, it's a solid, boom, it hits this line, melting occurs, and then if we pass that line, it's a liquid, okay? So here, and won't you be surprised to know that this is the normal melting point for H2O, and that should make sense to you, because that is the melting point for H2O. Or for ice or whatever it's also the freezing point, right? So what we now have we've learned a lot, is that this, of course, is melting, right, or fusion. This, of course, is freezing or solidification. So all your phase changes are hidden on this phase diagram. So if we continue this discussion and say, well, okay, well, now we would have melted and it's a liquid, and we would bring that over to the gas line and pull that number down. And what do you know? There's the normal boiling point for H2O. Okay, so again, we can put some more phase changes on here, that this is boiling, right, or evaporation. And this would be condensation. Okay, and then in this little area underneath here, we could talk about the other two that exist, that are the two less common ones. So from solid to gas, right, we've learned is sublimation. And from gas to solid, deposition. Okay, now a lot of times I will get the statement of, or I'll ask the question of, can water sublime? I shouldn't say water, sorry, can H2O sublime? Okay, well, that means, can H2O go from the solid state to the gas state bypassing the liquid state? And most students will say, of course it can't, because if we have an ice cube sitting on our desk, it's going to melt first, and that's completely true. But what we're not thinking about is the fact that we can have H2O exist outside of the range of normal, like, room temperature conditions. And so all we have to do is see, is there any place on this graph where I go from solid to gas without passing through the liquid? And I absolutely can. But notice, it's underneath the triple point. So can H2O sublime? Absolutely. What's the problem with it subliming? We're never going to see it in normal conditions, because the pressure would have to be less than this number, right? So can H2O sublime? Yes. Will you see it happen naturally? No way, because the pressure would almost be a vacuum situation. Okay, so a lot of information contained on a phase diagram. We learned triple point, we learned critical point, we learned how to identify the states of matter, how to do the changes. So the only other thing I want to show you is that the phase diagram for a different substance looks a little bit different. So here we have a phase diagram for a substance that is not H2O, right? And hopefully you could figure that out pretty quickly, because look at the triple point, right? Whew. Pressure's 5 times atmospheric pressure, right? So that's crazy high. This is not H2O. This is carbon dioxide. Okay, so the same thing occurs. This is the solid, this is the liquid, this is the gas. All right, we could talk about, where's melting. Well, this direction would be melting, right? This direction would be, freezing, okay? But a couple things to notice, that in this case, we could get H2O to exist. We could get CO2 to exist as a solid, as a liquid, and a gas. The temperature is pretty low, right? But the pressure is very high. Like we already said, 5 times normal atmospheric pressure. Very different from H2O. Remember, it was almost a vacuum. And so because this is CO2's graph, what we should pick up pretty quickly is the fact that CO2 is the thing we talk about that sublimes, that people know. It's dry ice, okay? Well, think about why this makes sense. It makes perfect sense because at normal conditions of 1 atm, right, as we raise the temperature, look at what process occurs. It's not melting. Right? Melting would be all the way up here. It's exactly sublimation. And so in this case, we're kind of proving the fact that, why does dry ice, solid CO2, sublime? Well, because the triple point for CO2 is way above normal room conditions. And so at conditions of 1 atm and room temperature, as we raise it up, of course sublimation is going to happen. So then of course I can ask the opposite question of, can you ever get CO2 to melt? Can you ever get CO2 in the solid state to go to CO2 in the liquid state? Now, if you've had any experience with dry ice, most students would say no, because it sublimes, right? But according to my phase diagram, I can absolutely get CO2 to melt. But it would have to be up here somewhere. What's the problem with that? The problem with that is not the temperature, right? It's the pressure. Look, you're talking about a pressure somewhere between 5 and 73. I don't know what it is because my drawing is not to scale. But it way exceeds the conditions of normal atmospheric pressure. So would you ever see CO2 melt sitting on your desk? No, because the pressure would be so high that we couldn't be there. Okay, we couldn't be in that same room. But if you were to pressurize CO2, could you get it to melt? Absolutely you could. So there's a lot of information contained on these phase diagrams. And we can answer some questions of things like normal boiling point, normal melting point, normal boiling point, normal melting point. We can also talk about the triple point and where would this what temperature and what pressure would all three phases coexist. And even more so than that, we can make some assumptions about, would this substance melt at room temperature and atmospheric pressure? Would it sublime, right? And you might not know the answer to that if we're not talking about these common substances, but if you had a phase diagram in front of you, you would be able to answer those types of questions.